Skyscrapers in the clouds, why don't they fall? Imagine standing at the bottom of a skyscraper so tall that its top disappears into the clouds. You look up, and up, and up. The building seems impossibly thin, impossibly heavy, and almost unnatural, a mountain made by humans standing on a patch of city ground. Now imagine the wind pushing against it. Not a gentle breeze. A powerful storm hitting the glass and steel hundreds of meters above the street. The clouds move around the tower. The building slowly sways, and yet it does not fall. So the question is simple but fascinating. How can something so tall, so heavy, and so exposed to wind stay standing? Why don't the skyscrapers collapse under their own weight? Why don't they snap in half? Why don't they tip over like a giant tree? The answer is not magic. It is engineering. And inside every skyscraper, hidden behind glass, concrete, elevators, luxury apartments, offices, and observation decks, there is a quiet battle happening every second. A battle against gravity. A battle against wind. A battle against earthquakes. A battle against time itself. Today we are going inside that invisible battle. We are going to discover why skyscrapers in the clouds do not fall. To understand skyscrapers, we need to start with the most obvious force of all, gravity. Gravity is always pulling the building downward. Every floor, every wall, every window, every elevator, every person inside, every piece of furniture, all of it adds weight. A skyscraper is not just tall. It is unimaginably heavy. A large tower can weigh hundreds of thousands of tons. So the first challenge is simple. How do you stop all that weight from crushing the floors below? The secret is that a skyscraper is not just a pile of floors stacked on top of each other. It is more like a skeleton. Just like your body has bones that carry your weight, skyscrapers have structural frames that carry loads. These frames are usually made of steel, reinforced concrete, or a combination of both. Steel is strong in tension. Concrete is strong in compression. When engineers combine them, they create a material system that can resist enormous forces. The weight of the building travels through columns, beams, walls, and cores. It moves downward from the roof floor by floor until it reaches the foundation. This journey of weight is called the load path. And if the load path is well designed, the building can safely transfer its weight into the ground. But that brings us to the next question. If the skyscraper is so heavy, why doesn't it simply sink into the earth? Because the building is not sitting on ordinary ground like a chair on a carpet. It stands on a foundation. And the foundation is one of the most important parts of the entire structure. You usually do not see it. Tourists do not take photos of it. It is not glamorous. But without it, the tower is nothing. The foundation spreads the building's weight into the earth below. In many skyscrapers, engineers use deep piles, huge columns of concrete and steel driven or drilled deep underground. Sometimes these piles go down until they reach solid rock. Sometimes they pass through layers of soil until they find ground strong enough to carry the load. Think of it like this. If you step into soft snow wearing regular shoes, your foot sinks. But if you wear snowshoes, your weight spreads over a larger area and you stay on top. A skyscraper foundation does something similar. It spreads and anchors the load so the building does not sink, tilt, or shift dangerously. But gravity is only half the story. In fact, for very tall buildings, the most dramatic enemy is often not gravity. It is wind. Near the ground, wind is slowed down by trees, smaller buildings, cars, signs, and the rushness of the city. But hundreds of meters above the street, wind is much stronger. It can hit a skyscraper with huge force. And it does not just push once. It pushes again and again. It changes direction. It creates pressure. It creates suction. It wraps around the building and forms swirling patterns called vortices. These vortices can make the tower sway from side to side. This is why skyscrapers are not designed as stiff, unmoving objects. That may sound surprising. But a perfectly rigid skyscraper would be dangerous. If a building could not move at all, forces would build up inside it until something cracked or failed. Instead, skyscrapers are designed to move safely. They bend, they sway, they flex. A tall tower in strong wind can move by centimeters or even more at the top. People inside may not notice it most of the time. But the movement is real. And that movement is not a weakness. It is survival. A tree survives wind because it bends. A skyscraper survives wind because it is engineered to bend in a controlled way. But controlled movement is not enough. Engineers must also make sure the movement does not become uncomfortable for people inside. A tower could be structurally safe but still feel unpleasant if it sways too much. Imagine working on the 90th floor and feeling the room slowly shift back and forth. Your coffee ripples. The hanging lamps move. Your stomach begins to complain. So skyscraper design is not only about preventing collapse. It is also about human comfort. One of the most famous solutions is called a tuned mass damper. The name sounds complicated, but the idea is beautiful. A tuned mass damper is a huge weight placed high inside a building. It may be a giant steel ball, a massive concrete block, or a heavy suspended system. When the building sways one way, the damper moves in the opposite direction. This counter motion absorbs energy and reduces the movement of the tower. It is like giving the skyscraper a giant internal balance system. One of the best known examples is Taipei 101 in Taiwan, which has a massive golden tuned mass damper visible to visitors. During strong winds or earthquakes, the damper helps reduce the building's motion. But dampers are only one tool. Modern skyscrapers also use clever shapes. At first glance, the shape of a skyscraper might look like an artistic choice. A twisted tower, a tapered tower, a tower with setbacks, a tower with holes, curves, or rounded corners. But many of these shapes are not only about beauty. They are about controlling wind. When wind hits a simple rectangular tower, it can create powerful repeating vortex patterns. These patterns can push the building rhythmically, almost like someone pushing a swing at just the right time. If the wind's rhythm matches the building's natural rhythm, the movement can increase. This is called resonance. And resonance is something engineers work very hard to avoid. So they disrupt the wind. They change the building's profile as it rises. They round the corners. They twist the tower. They taper the structure. They add setbacks. They create openings. All of these design choices can confuse the wind and reduce dangerous rhythmic forces. A skyscraper is not just standing in the air. It is negotiating with the air. Now let's talk about the core. Most tall buildings have a strong central core. This core often contains elevators, stairwells, mechanical shafts, and emergency routes. But structurally, it is much more than a hallway for elevators. The core acts like the spine of the building. It helps resist bending, twisting, and lateral forces. In many skyscrapers, this core is made of reinforced concrete. It is thick, heavy, and extremely strong. Around it, the building may have columns and perimeter frames that help carry loads. Together, the core and outer structure create a system that can resist gravity and wind. Some towers use what engineers call an outrigger system. Imagine the central core as the trunk of a tree. Now imagine strong horizontal arms reaching from the core out to the perimeter columns. These arms connect the inner spine to the outer frame. When wind tries to bend the building, the outriggers help the core and perimeter columns work together. This makes the tower stiffer and more efficient. It is one reason modern supertall buildings can reach such extreme heights. But what about earthquakes? Wind pushes from the side. Gravity pulls downward. Earthquakes are different. During an earthquake, the ground itself moves. That means the foundation moves first, and the building has to respond. A short, stiff building may shake quickly. A tall skyscraper tends to move more slowly because it has a longer natural period. This can sometimes help depending on the type of earthquake waves. But earthquakes are complex. They can cause sideways shaking, vertical shaking, twisting, and repeated cycles of stress. So skyscrapers in earthquake zones need special design strategies. They may use flexible structural systems. They may use dampers. They may use base isolation in some cases. They may include ductile materials that can deform without suddenly breaking. This is extremely important. A safe building is not one that never cracks. In extreme events, some damage may happen. But the goal is to avoid sudden collapse. Engineers design buildings so that if they are pushed beyond normal conditions, they fail slowly, visibly, and in controlled ways, giving people time to escape. This idea is called ductility. It is one of the most important concepts in earthquake engineering. A brittle structure can break suddenly like glass. A ductile structure can bend, stretch, crack, and absorb energy before failure. That difference can save lives. Now let's zoom in on the materials. Steel is one of the great heroes of skyscraper history. It made tall buildings possible. Before steel frames, buildings relied heavily on thick masonry walls. The taller the building, the thicker the walls had to be at the bottom. At a certain point, the lower walls would become so thick that the building would lose usable space. Steel changed everything. A steel frame could carry the weight without massive stone walls. This allowed architects to build taller and open up the exterior walls for windows. That is how the modern skyscraper was born. But today, concrete is just as important. High-strength reinforced concrete is used in many supertall buildings. Concrete handles compression very well, while steel reinforcement helps it handle tension. Together, they create strong columns, cores, and walls. Modern concrete can be engineered to reach incredible strength. It can be pumped hundreds of meters upward during construction. It can be designed to cure properly under difficult conditions. It can resist fire, pressure, and long-term loads. And that brings us to another hidden challenge. Skyscrapers do not just need to survive one big storm. They must survive decades. The weight of the building is always there. Day after day, year after year, concrete can slowly deform under long-term pressure, a process called creep. Materials expand and contract with temperature changes. Steel can heat up and cool down. Wind loads repeat thousands and thousands of times. Water tries to enter. Corrosion tries to weaken metal. Fire safety systems must remain reliable. Elevators must keep functioning. Foundations must stay stable. A skyscraper is not a finished object. It is a living system that must be monitored, maintained, repaired, and inspected. This is one reason engineering is not only about design. It is also about maintenance. A neglected skyscraper is a risk. A well-maintained skyscraper can stand safely for generations. Now let's return to the big visual question. Why doesn't a skyscraper tip over? After all, when wind pushes near the top, it creates a turning effect. This is called an overturning moment. Imagine pushing the top of a tall bookshelf. If the base is too small or too light, it tips. So why does a skyscraper not do the same? Because the foundation and structure are designed to resist that turning effect. The building's weight helps hold it down. The foundation anchors it. The piles transfer forces deep into the ground. The structural frame distributes tension and compression. On one side, columns may be squeezed. On the other side, they may be pulled. The entire building works as a connected system. It is not one piece trying to stand alone. It is thousands of components sharing the forces. This is one of the most beautiful ideas in engineering. Strength comes from connection. A single beam may be weak. A single column may fail. But when thousands of elements are arranged correctly, connected properly, and supported by a strong foundation, they create something extraordinary. A tower that can rise through clouds. But there is another force that many people forget. Twisting. Wind does not always hit a building evenly. It can hit one corner harder than another. An earthquake can move the base in complex ways. Uneven shapes and uneven stiffness can make a building rotate slightly. This is called torsion. Torsion is dangerous because it can concentrate stress in unexpected places. So engineers study not only how a building bends, but how it twists. They use computer models. They test scale models in wind tunnels. They simulate storms, earthquakes, pressure zones, vibrations, and material behavior. Before a skyscraper is built, it may already have survived thousands of virtual disasters. In a wind tunnel, a small model of the tower is placed in carefully controlled airflow. Sensors measure pressure and movement. Engineers test different shapes. They might discover that rounding one corner reduces wind forces, or that changing the tower's taper improves comfort, or that adding setbacks breaks up dangerous vortex patterns. This is where architecture and engineering meet. The most elegant skyscrapers are not just drawn. They are tested. The sky helps design them. Now, let's talk about something that sounds strange. A skyscraper has a rhythm. Every structure has a natural frequency. If you push it, it wants to vibrate in certain ways. A guitar string has a natural frequency. A bridge has one. A tower has one too. The taller and more flexible a building is, the slower its sway can be. This rhythm matters because outside forces can interact with it. Wind gusts, vortex shedding, machinery, or earthquakes can excite the building's natural motion. If that motion grows too large, it becomes a problem. So engineers tune the building. They adjust stiffness. They adjust mass. They add damping. They change the shape. They make sure the tower's rhythm does not become dangerous. In a sense, designing a skyscraper is like composing music. But the instruments are concrete, steel, glass, wind, and gravity. And the audience is everyone inside. Now you may ask, if skyscrapers can move, why don't their windows crack? Why don't pipes break? Why don't elevators jam? The answer is that everything must be designed for movement. The facade, the outer skin of glass and metal, is not simply glued to the building like a rigid shell. It is attached with systems that allow small movements. Joints can expand and contract. Glass panels are designed to handle pressure differences and building motion. Pipes and mechanical systems include flexible connections. Elevator rails are installed with strict tolerances. Fire safety systems, stairwells, and emergency routes must remain functional even when the building moves. In a tall tower, movement is not an accident. It is expected. The entire building is detailed around that expectation. This is why skyscraper engineering is so difficult. It is not enough to calculate the main structure. Every connection matters. Every bolt matters. Every weld matters. Every joint matters. A tower can be designed correctly on paper but still become dangerous if built poorly. Construction quality is part of structural safety. Skyscrapers require intense coordination. Architects design the form and spaces. Structural engineers design the load-bearing system. Geotechnical engineers study the ground. Wind engineers study air pressure and movement. Mechanical engineers design heating, cooling, ventilation, and elevators. Fire engineers design safety systems. Construction teams turn plans into reality. Inspectors check the work. And all of them must cooperate. Because at 600 meters in the sky, small mistakes can become big problems. Now let's look at one of the most famous skyscraper ideas, the tube structure. For a long time, skyscrapers used interior frames. But as buildings became taller, engineers needed more efficient ways to resist wind. The tube concept treats the outer perimeter of the building like a hollow tube. Instead of relying only on internal columns, the exterior columns and beams work together as a stiff shell. This is much stronger against sideways forces. Imagine a cardboard tube. It is light, but surprisingly strong because material is placed around the outside. A skyscraper tube works in a similar way. Different versions of this idea include framed tubes, braced tubes, bundled tubes, and tube-in-tube systems. These systems helped make many iconic tall buildings possible. The basic idea is simple. Put strength where it is most useful. For resisting bending, the outer edges of a structure are extremely important. That is why perimeter columns can be so powerful. They are far from the center, giving the building a wider structural stance. The wider the stance, the better the tower can resist overturning. This is also why many skyscrapers are not just tall sticks. Their bases are often large, complex, and deeply integrated with the ground. Some towers use setbacks that reduce area as they rise. This can lower wind forces at higher levels. It can also create a stable visual and structural form. The building becomes more like a mountain, broad below, slimmer above. But not every skyscraper follows that shape. Some are slender, very slender. These are among the hardest to design. A slender tower has a small width compared with its height. That means wind can make it sway more easily. To make slender towers work, engineers need advanced structural systems, high-strength materials, dampers, careful mass distribution, and extremely precise analysis. In some luxury residential towers, controlling human comfort becomes one of the biggest challenges. A building can be safe but still too uncomfortable if residents feel motion too often. So engineers measure expected acceleration, not just displacement. Displacement is how far the tower moves. Acceleration is how strongly people feel that motion. Humans are sensitive to acceleration. A slow, gentle sway may be barely noticeable. A quicker movement can feel disturbing even if the distance is small. So skyscrapers are designed not just for strength, but for sensation. The human body becomes part of the engineering equation. Now, let's imagine a storm. At street level, umbrellas flip inside out. Rain hits sideways. People rush indoors. But 300 meters above the ground, the wind is much stronger. The tower begins to sway. Deep underground, piles transfer forces into soil and rock. In the core, concrete walls resist bending. At the perimeter, columns go into compression and tension. Outriggers engage, dampers move in opposition. The facade flexes at its joints. The elevators continue operating within safety limits. Sensors may record the motion. To a person outside, the building looks still. But inside the structure, a massive invisible system is working. That is why it does not fall. Not because it is rigid, because it is intelligent. Not intelligent like a person, but intelligent in design. Every force has a path. Every movement has a limit. Every danger has been considered. At least that is the goal. Of course, no structure is invincible. Engineering is not about making impossible promises. It is about managing risk. Every building is designed for certain conditions. Normal loads, extreme winds, expected seismic activity, fire scenarios, evacuation requirements, material limits, safety factors. A skyscraper is designed with margins because the real world is unpredictable. Wind may be stronger than expected. Soil may behave differently. Construction errors may happen. Materials may age. Future changes may add weight. That is why codes, inspections, maintenance, and engineering ethics matter so much. A skyscraper is a promise to thousands of people. A promise that they can work, live, sleep, eat, meet, and dream hundreds of meters above the ground safely. Now think about the psychological side. Humans did not evolve to live in towers. For most of history, the tallest things we saw were trees, cliffs, mountains, and clouds. Then we started building upward. First with stone towers and cathedrals. Then with steel frames and elevators. Then with glass, concrete, computers, and wind tunnels. The skyscraper is one of the clearest symbols of modern civilization. It says, we understand materials. We understand forces. We understand the ground. We understand the wind. We can build vertically. But the higher we go, the more nature reminds us that we are guests in the sky. The wind is stronger. The temperature changes. Lightning becomes a real design issue. Evacuation becomes harder. Water pressure systems become more complex. Elevators become engineering marvels. Even getting concrete to the top becomes a challenge. A skyscraper is not just a tall building. It is a vertical city. It needs transportation, energy, water, air, communication, safety, and structure. Everything that exists horizontally in a city must be reorganized vertically. And the structure must hold it all. Let's talk about elevators for a moment. Without elevators, skyscrapers would not make sense. No one wants to climb 100 floors every day. Modern elevator systems are carefully planned because they affect the entire building. Elevator shafts take space. Elevator speed affects comfort. Too many elevators waste floor area. Too few elevators create long waits. In supertall buildings, engineers may use sky lobbies, double-deck elevators, express elevators, and advanced control systems. But elevator shafts also influence structure. They are often located in or near the central core. So the same zone that moves people vertically also helps the building stand. That is elegant. The building's spine is also its transportation highway. Now, fire safety. One of the biggest fears in tall buildings is not only collapse, but evacuation. How do you get people out of a building that may have 80, 100, or 150 floors? The answer includes fire-resistant materials, protected stairwells, sprinkler systems, smoke control, fire-rated doors, refuge areas, alarms, communication systems, and emergency planning. The structure itself must resist fire long enough for evacuation and firefighting. Steel loses strength at high temperatures, so it is protected with fireproofing materials. Concrete has natural fire resistance, but it also must be detailed properly. A skyscraper is designed in layers of safety. Prevent fire, detect fire, control fire, protect escape routes, maintain structural stability, help firefighters respond. No single system is enough. Safety comes from redundancy. That word redundancy is central to skyscraper design. It means the building should not depend on just one element. If one component is damaged, other components should help carry the load. This does not mean anything can fail without consequences, but it means the structure has backup paths. Redundancy makes buildings more resilient. A skyscraper is not a chain where one broken link destroys everything. It should be more like a web where forces can redistribute. This is especially important in extraordinary events. Now, what about the glass? Many people look at skyscrapers and see fragile glass boxes. But the glass is not ordinary window glass. Facade systems use engineered glass, frames, seals, anchors, and pressure-equalized designs. The glass must resist wind pressure, temperature changes, rain, and movement. It also affects energy use. Too much sunlight can overheat the building. Too little insulation wastes energy. So modern skyscraper facades often include coatings, double or triple glazing, shading systems, and carefully designed thermal performance. The outer skin of a skyscraper is not just decoration. It is climate control. It is weather armor. It is part of the building's identity. And sometimes it also helps with structure. Now let's return to the dramatic phrase, skyscrapers in the clouds. Clouds make skyscrapers look mysterious. But clouds also remind us of something important. At great height, the environment changes. Wind speed increases. Air pressure changes. Temperature can be different. Lightning risk increases. Maintenance becomes harder. Workers who clean windows or repair facades operate in extreme conditions. Cranes used during construction must deal with wind limits. Even the building process becomes a fight against height. During construction, the unfinished tower may be more vulnerable than the completed one. Why? Because some stabilizing systems are not fully connected yet. The final mass distribution is not complete. The core may rise ahead of the floors. Temporary supports may be needed. Construction sequence matters. Engineers do not only design the final skyscraper. They also design the path to get there. A building must be safe while it is being born. That is an incredible thought. Now imagine concrete being pumped upward through pipes. At ground level, mixers arrive. Pumps push heavy wet concrete higher and higher. Workers place reinforcement steel. Forms shape the concrete. Floor by floor, the tower grows. Surveyors check alignment, because tiny errors can accumulate. If each floor is slightly off, the top could drift out of position. So construction uses precise instruments, caves, lasers, and constant measurement. A skyscraper is not just big. It must be accurate. Accuracy is safety. Now let's look at foundations again, because they are so important. The ground under a city is not always simple. Some cities have rock near the surface. Others have soft soil, clay, sand, fill, or waterlogged ground. A skyscraper in Manhattan faces different foundation conditions than a skyscraper in Dubai, Shanghai, or Kuala Lumpur. Geotechnical engineers drill into the ground before construction. They study soil layers. They test strength. They analyze settlement. Settlement means the building slowly moves downward as the ground compresses. Some settlement is expected. Uneven settlement is the real danger. If one side settles more than the other, the building can tilt or develop stress. So foundations are designed to control settlement. The goal is not always zero movement. The goal is predictable, safe movement. That is a theme in skyscraper design. Not zero force, managed force. Not zero movement, controlled movement. Not zero risk, reduced risk. Now, why are skyscrapers often made with triangles, braces, or diagonal elements? Because triangles are extremely stable shapes. A rectangle can deform into a parallelogram if its corners are not stiff. But a triangle holds its shape. Diagonal bracing uses this principle. In some skyscrapers, you can see giant diagonal braces on the exterior. These braces help resist lateral forces. They carry tension and compression. They make the building stiffer. Sometimes the structure becomes part of the architecture. You can look at the building and see how it stands. That is one of the most satisfying things in design, when beauty and function become the same thing. But many structural systems are hidden. Behind walls, inside cores, under floors, below ground. The public sees the skilling. Engineers see the force diagram. And that is the difference between looking at a skyscraper and understanding it. Now let's answer the question in the most direct way. Why don't skyscrapers fall? Because gravity is carried down through a carefully designed structural skeleton. Because foundations transfer enormous loads into strong ground. Because wind forces are reduced by shape and resisted by cores, frames, braces, tubes, and outriggers. Because towers are allowed to sway safely instead of fighting movement with impossible rigidity. Because dampers absorb energy. Because materials are chosen for strength, ductility, and durability. Because engineers test models, run simulations, follow building codes, and include safety factors. Because every serious skyscraper is designed as a complete system. Not just a building. A system. But there is one more answer. They do not fall because people learned from failure. Every field of engineering carries history. Bridge collapses, fires, earthquake damage, wind failures, foundation problems, facade failures. Every disaster teaches painful lessons. Building codes improve. Materials improve. Analysis improves. Construction practices improve. Skyscrapers stand today because engineers study what went wrong yesterday. Progress in engineering is often written in caution. This is why humility matters. A skyscraper may look like a symbol of human arrogance, a tower reaching into the sky. But the best skyscraper engineering is actually an act of humility. It respects gravity. It respects wind. It respects earthquakes. It respects fire. It respects the ground. It does not pretend nature is weak. It assumes nature is powerful and designs accordingly. That is the real genius. Not conquering nature, working with it. A skyscraper survives because it moves with the wind, anchors into the earth, spreads its loads, absorbs energy, and gives forces a safe path to travel. The tower may seem silent, but it is always responding. Every gust, every temperature change, every elevator ride, every crowd of people, every storm, every tiny vibration, the building feels all of it. And if it is designed well, it calmly carries on. So the next time you stand beneath a skyscraper and look up into the clouds, remember this. You are not just looking at glass and steel. You are looking at physics made visible. You are looking at mathematics turned into shelter. You are looking at thousands of decisions stacked into the sky. You are looking at a structure that survives not because it is invincible, but because it understands its enemies. Gravity pulls, wind pushes, the earth shakes, time wears everything down. And still the skyscraper stands. Not frozen, not fearless, but balanced, flexible, anchored, alive with invisible forces. That is why skyscrapers in the clouds do not fall. And maybe that is what makes them so fascinating. They are among the largest things humans build, yet their survival depends on details most people will never see. A bolt, a weld, a joint, a pile deep underground, a damper hidden near the top, a curve in the facade, a calculation checked again and again, a tiny movement allowed at exactly the right place. The skilling is not held up by height. It is held up by understanding. And the higher we build, the more that understanding matters.